Okay, in this video today, we're going to continue on and do a second day talking about mole-to-mole stoichiometry. Should be the guided notes that you should have in front of you to follow along with. Now, the reason we're doing 2 days of this, make sure everybody gets this down before we move on to some harder problems to where we're going to add steps to these problems. And also, these are worded a little bit more difficult, so make sure everyone understands. But first, to review kind of what we've talked about so far in stoichiometry, we've used examples where we were making a sandwich and we figured out from a basic recipe for making one sandwich how much would we need to make 20 sandwiches, and then we relate this to chemical reactions the same way. First of all, this reaction right here tells me that iron, which is Fe, reacts with O2, which is oxygen gas, and it produces iron 3 oxide, which is the formula for that is Fe2O3. First step always in these problems is we have to have a balanced equation. Our balanced equation tells us the ratios that these elements react with one another, ratio of molecules, or what we're going to call moles, to simplify things, and there's certain amounts. So it's a recipe to go by. It's the simplest recipe that's been reduced down. So first I will need to balance this. We're going to review how to balance equations. It's been about a month since we've done that. Now to balance equations, I draw a line down the middle. I'm going to label the elements that make up this reaction. I have iron and I have oxygen on the left, and I got same on the right. Then I'm going to count the number of the number of atoms on each side of the arrow. So on the left I have 1 iron, I have 2 oxygens. On the right I have 2 irons and I have 3 oxygens. Alright, so I notice that my equation is not balanced. If I have 2, I'm going to start with my irons. If I have 2 on the right, and remember I can only put numbers in the front here to balance these equations. I cannot change subscripts, and I cannot add a coefficient in the middle of a compound, only at the front. So first I'm going to balance my irons. I got 2 on the right, I need 2 on the left. I'm going to put a 2 in front here, and then I got 1 iron atom. That's going to make me 2 times 1, so make me have 2. So the irons are balanced now. Then I look at the oxygens. I got 2 on the left, 3 on the right. I need to have, if I have a 2 and a 3, the way I would do this is to find the least common multiple. The least common multiple of 2 and 3 is 6. So I need to have 6 on each side. So on the left I have 6, I will need to put a 3 here because 3 times 2 would give me 6. On the right I will need to put a 2 in front there because 2 times 3 would give me 6 oxygens, and 2 times 2 would give me 4 irons. But my irons change, so I need to go back to the left and I got to change my irons to 4. So that's the balanced equation. That now, that changes the irons to 4, so then I check 4 and 4, 6 and 6. That should be the balanced reaction. So in nature, in the simplest way that iron 3 oxide is made, it's made this way. And remember, the 4 molecules of iron reacts with 3 molecules of O2 to produce 2 molecules of Fe2O3. But we're going to say that these numbers tell us moles. That's a certain amount. So we're going to say that 4 moles of Fe, and these are ratios, remember, of how they react. Reacts with 3 moles of O2, and that produces 2 moles of Fe2O3. That's the simplest way this reaction happens in these ratios. Well, maybe I don't want to make 2 moles of Fe2O3. Maybe I want to make, 200 moles of it, or so forth. These are ratios, though. So let's say I have, instead of 4 moles of Fe, let's say I have 8 moles of Fe. How's that going to change my moles of O2 that react with it? Well, it's a 4 to 3 ratio. So how would that be if I had 8 moles of Fe? That would have to be 6, right? Because 8 and 6 would reduce down to 4 and 3. Alright, and then how many iron oxides would that be if you had 8 moles of Fe and 6 moles of O2? Well, it's a 4:2 ratio between Fe and Fe2O3, so it's half of Fe2O3. That would have to be a 4 there. So this reaction also happens, 8 moles of Fe reacts with 6 moles of O2 to produce 4 moles of Fe2O3. So the balance equation is just the simplest whole number ratio, reduced down. How about if I have, let's see, if I had, instead of, if I had 12 of these, how would that ratio change? Well, I can always figure this up how we did our problems yesterday. We'll look some more here in a minute, but just thinking about it, if that reduces down to 4 and 3, that would, then a 12 would have to be 12 and 9, right? And then for iron oxide, it's a 4:2 ratio, which is a 2:1. Same thing, it reduces down. So 12, it would be 6. So every time 12 moles of iron reacts, 9 moles of O2 reacts with it, and it produces 6 moles of Fe2O3. And I could go on and on. How about if I have, 0.25 moles of Fe? How would these numbers right here be? So, and then when I get into cases with this like this, though, I can't really do it in my head. I would have to do some math, which is what we talked about yesterday. And that's what we're going to be talking about today. So, stoichiometry is the measuring of elements and compounds in a chemical reaction. It involves calculations to determine the amounts of product formed and the amounts of reactants needed. It's important to remember that solving stoichiometry problems is very similar to following a recipe. Once you know the recipe, you can modify it using the same ratios to make the product for more or less people. So mole ratios, they are what we use. They are our conversion factors, how we convert from moles of one substance to moles of another substance. So we use mole ratios to convert from moles of one substance to moles of another substance. We get mole ratios from the balanced chemical reaction. Write down all possible mole ratios for the following reaction. So what it means by mole ratios is how does each thing compare to the other according to my balanced equation. Well, in this case, that would be a 1 there since there's not a coefficient. Every time that 1 mole, and I'm not going to write out the mole, but just 1 mole of Fe2O3 reacts, 3 moles of CO react with it. I know that according to my balanced equation, it's a 1:3 ratio. Also, every time 1 mole of Fe2O3 reacts, 2 moles of Fe are produced. Also, every time 1 mole of Fe2O3 reacts, you get 3 moles of carbon dioxide. Some other possible mole ratios, if I look at the other reactant, if I have 3 moles of CO, I get 2 moles of Fe. Also, if I start with 3 moles of CO, I get 3 moles of CO2. Now, is that all of the mole ratios? I think there would be one more. I can relate my 2 products to one another. Every time 2 moles of Fe are produced, I get 3 moles of CO2. And so I've related my 2 reactants to one another, my reactants to both my products, and both my products to one another. So when I solve problems, I can figure out, starting given my number of moles of my reactants and figure out the number of moles of my product, or I can be given my numbers of moles of my product and figure out my number of moles of a reactant, or I could be given the moles of reactant and figure out the number of moles of the other reactant that's going to react with it. So it doesn't matter. I'm just going to be comparing 2 things that are part of a chemical reaction in these problems. So let's look at the first example. Steps. First, always mole to mole stoichiometry. Balance the equation and calculate the mole ratios. Number 2, find the moles of the given. Number 3, calculate the moles of the wanted. by using, that's your unknown, moles of the wanted, by using mole ratios or by setting up a ratio proportion. Remember, I showed you two different ways to work these. So my problem says, how many moles of iron can be made from Fe2O3 by use of 18 moles of carbon monoxide, which is CO, in the following reaction? First of all, I gotta look, see if I got a balanced reaction. And I don't when I look at the number of atoms. First step is I'm gonna balance this reaction. Sometimes I'll give you the balance equation, but if I don't, you have to balance it before you work these. So that's why we're reviewing over this. On the left, the elements that make this up, I have iron, I have oxygen, and I have carbon. On the right, I have the same elements, iron, oxygen, and carbon. So then I count the number of atoms. On the left, I have 2 irons. Oxygens, I got 3, that's part of Fe2O3, but I got 1 more here for a total of 4. Carbons, I have 1. On the right, I have 1 iron, I have 2 oxygens, and I have 1 carbon. So this one's kind of difficult to balance, so I'm helping you with this one. If you run into a situation, most of them are not going to be like this one. Most of them are going to be easier. Even if they look like they're hard to balance, they work out pretty easy. First I'm going to balance my irons. I got 2 on the left, I need 2 on the right. I got to put a 2 right there, and I balance my irons. Then my oxygens. Now you would think, I got 4 on the left, and you got 2 on the right, I just need to go put a 2 right here. But that changes my oxygens to 4, which balances them, but it changes my carbons to 2. So I got to go back to the other side and balance my carbons. So I go back to the other side and put 2 there, and it makes my carbons equal 2, but it's going to change my oxygens. I got 3 that's part of the Fe2O3, and then plus 2 more, that gives me 5, which messes everything up. Now, when I run into this situation right here, very rarely, this is 1% of the time you're going to run into one like this where it's all messed up. What you would do in this situation is kind of just put in some numbers and try to balance it without, just kind of guess on some numbers. And what I would do was, since it messes up my oxygens here, my oxygens are split, I would change this number and this number right here go up 1. So instead of a 2, put a 3 there. And that's going to make your oxygens be 6 and your carbons be 3. And then go and balance your carbons. If you put a 3 in front of here to balance it, make sure you have 3 carbons, and then look what it does to your oxygens. You got 3 that's part of Fe2O3. Then you got 3 that's part of CO, 3CO. That makes you have 6, and they balance out. I don't know why this one works out that way, but I will not give you one like that on a test or anything like that you'd have to balance that's like that. But that's the way I would handle that. Now I'm going to erase this part here. I have my balanced equation. Now I want to work the problem. So what the problem tells me, my balanced equation tells me that every time 1 mole of Fe2O3 reacts, it reacts with 3 moles of carbon monoxide, that's 3CO, and it produces 2 moles of Fe and 3 moles of CO2. So let's see what our problem asks. It asks how many moles of iron, that's going to be my unknown, my wanted, moles of Fe, can be made from Fe2O3. It says tell me that Fe2O3 by use of 18 moles of carbon monoxide. 18 moles of carbon monoxide is my given. So I'm given 18 moles of carbon monoxide. I'm going to go ahead and write that down. 18 moles of CO. I'm going to be multiplying that by something. Put that over 1. Now I want to go to moles of iron. Now what's the balance equation tell me about these things? How does it relate the two? Iron and carbon monoxide. It tells me that 3 moles of CO is equal to 2 moles of Fe. And you notice in the problem it says can be made from Fe2O3, but it doesn't give me a number, it doesn't ask me to solve for that, it's just giving me more information than I need. This is my conversion factor right here. So I'm going to multiply by it. What's going to go on top? What's going to go on bottom? Well, I'm looking for moles of iron, so I want to put my 2 moles of Fe on top and my 3 moles of CO on bottom. That way moles of CO cancel, and my units are going to be moles of Fe, which is what I need. Then I do the math. 18 times 2 equals 36. 1 times 3 on bottom equals 3. 36 divided by 3 equals 12. My units are going to be moles of Fe. Now that's the way of working it when I use a mole ratio. Now I'm going to work it the other way. Now it tells me that I have 18 moles of carbon monoxide. So I'm going to put the 18 underneath the carbon monoxide, put that underneath the CO, and it's asking me how many moles of Fe can be produced. I'll put the X under that. And then I'm going to separate proportion with my coefficients for my balance equation. That would be 3 over 18 equals 2 over X. Cross multiply, 3X equals 36. Both sides by 3, and it equals 12. So either way you want to work that problem, whichever way is easier for you is what I would suggest. So let's look at the next one. How many moles of H2O are produced when 6 moles of O2 is consumed in burning methyl alcohol, CH3OH, according to the following equation? Alright, so I need to balance this first. This is made up of carbon, it's made up of hydrogen and oxygen. I have 1 carbon, I have 4 hydrogen, I have 3 oxygens on the left. Over here I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. So I'm going to start with my hydrogens, and hopefully it balances out right. I put a 2 right here. It's going to balance my hydrogens out to make me have 4. And it's going to balance my hydrogen up. It's going to change my oxygens. Now I got 4 oxygens. And now I've run into a problem again with this problem right here that I'm going to kind of have to guess at. So when I work this one out, if I need the, say, if I go and I work out and I should have worked this problem before I started this video. If I was to try to make myself have a different number, the 4 and 3 is not going to work out. If I just play around with this, and like I said, I won't give you any on a test like this. If I put that in there, now that makes my carbons equal 2. It makes my oxygens equal 6. If I go and I balance these over here now, and I put a 2 there, and I put a 2 there, then that's going to make me have 8 hydrogens. And it's going to change these oxygens to a total of 4. And I can't, that's not going to work. So let me try something else. Okay, if I go back, and I look at this one, and really because of time, I didn't want to get caught up doing one of these like this. If I have 4 auctions there, and I'm just going to look up and see what I had this down because I don't want to waste time doing this one through. That's a bad example. Like I said, I won't give you one like that. So it's actually 2-3, 2-4. So I'm just going to give you this one. Because that one's a very hard one to balance out, and I probably have to play around with it for a while to get that, and I don't want to waste time balancing one that I would never give you on a test anyway. So if we have this one, that should balance it out. And it tells me that how many moles of H2O are produced when 6 moles of O2 are consumed in burning methyl alcohol according to the following equation. So it's asking me for moles of H2O. That's my wanted. And it gives me 6 moles of O2. So it says I have 6 moles of O2. Put that over 1. And then I got to relate, I got to use a conversion factor from moles of O2 to moles of H2O. Well, my balance equation says that every time 3 moles of O2 react, then I get 4 moles of H2O. That's my conversion factor. I'm going to multiply by that. So I need the 3 moles of O2 on bottom. I need the 4 moles of H2O on top. That way my moles of O2 cancel. I'm left with moles of H2O. 6 times 4 is 24. 1 times 3 is 3. 24 divided by 3 is 8. So that's going to be 8 moles of H2O. It gives me information like burning methyl alcohol, CH3, but I don't use that in the problem. So it's just giving me more information than I need. Now, I can erase this and do it the other way. Do it in proportion. And like I said, I'm just going to start working these problems just one way. And hopefully by now you have it dialed down. You can do it your way, and I can, pick which way. I'm just going to show how to work it. And again, I'm given 6 moles of O2. I put that underneath the O2. Put that underneath there. I'm looking for moles of H2O, so I put an X underneath H2O, and I set up a proportion. 3 over 6 equals 4 over X. Solve for X, which is going to give me moles of H2O. Equals 3X equals 24 divided by 3. X is going to be equal to 8 moles of H2O. Alright, moving on. This one a little bit more difficult. And maybe this one, when I bounce this equation, will work out better than the other ones. And I think it will. This one looks tough, but it'll work out better. First step, I need to bounce my reaction. This one has polyatomic ion, and I could leave it as a polyatomic ion in there, but since I have oxygen in both of my reactants and both of my products, I'm going to split these up. So this is made up of iron and oxygen, calcium, phosphorus. Now I'll start counting. On the left I have 1 iron. Oxygen I have 3, that's part of Fe2O3, but then I have this formula here. I got O4 with a 2 on the outside. 4 times 2 is 8. Remember, whatever's on the outside of the parentheses multiplies everything on the inside. So that would give me 8, and then 8 plus 3 gives me 11. Calcium, I have 3 of those. Phosphorus, I have 1 on the inside times 2 that's on the outside, gives me 2. All right. On the right, I have 1 iron. I have oxygen. I got 4. That's part of the Fe, PO4. And I got one more CaO, so it gives me a total of oxygens of 5. Calcium I have 1. Phosphorus I have just 1. So when I balance this, I'm going to start with my calciums. If I look, I go to the left side and I put a 3 here. It's going to change my calciums to 3, but it's going to change my oxygens to, I got 4 right here plus 3 more. It's going to change those to 7. And if I go and I try to balance out my phosphorus ones in, if I go and I put I got 2 on the left, I need 2 on the right. If I put a 2 here, and that's going to also, my irons I had 2 in the beginning, so if I balance my irons, that's going to give me 2 irons. It's going to give me phosphorus, I have 1 right now, it's going to give me 2 of those. It's going to change my oxygens. I got 2 times 4 is 8, plus 3 times 1, 3 more of them. That gives me 11, and that balances out. So that works out a lot better than the last one about balancing out. So the way this reaction, and then I can erase all this. Now this reaction says that 1 mole of Fe2O3 reacts with 1 mole of Ca3PO42, it's calcium phosphate, to produce 2 moles of FePO4 plus 3 moles of calcium oxide. Alright, so now I look and I read the problem. It says how many moles of calcium oxide, so that's my wanted, moles of CaO, this right here, will be produced when 2.4 moles of iron 3 oxide, that's Fe2O3, that's this right here, and I'm looking for reacts with calcium phosphate. Now it tells me it reacts with calcium phosphate, but it doesn't give me numbers. That's just giving me more information than I know. So what it's saying is I have 2.4 moles of Fe2O3, and I'm trying to get to moles of CaO. So what's my balance equation tell me? Well, tell my balance equation, it's relating this and this. It tells me it's a 1 to 3 ratio. It tells me that when 1 mole of Fe2O3 reacts, I get 3 moles of CaO. So I'm going to multiply by that. And what's going to go on top, what's going to go on bottom? I'm looking for moles of CaO, so I'm going to put the 3 moles of CaO on top. I'm going to put the 1 mole of Fe2O3 on bottom. My moles of Fe2O3 are going to cancel. Then I do the math. I'll put that over 1. 2.4 times 3 would give me, what would that be? 7.2 over 1, which is divided it, you get 7.2. My units are going to be moles of CaO. So it's worked the same way the problems were worked yesterday, except it gives you a little bit more information and the equations are a little bit harder than the ones yesterday. And it gives you a little bit more information in the problem that you have to pick out what is it you're given and what are you looking for, and those two things are what that matters. So in this problem, the Ca, that right there wouldn't matter, and this right here wasn't part of the problem either. It was just these two things. Alright, I could have also did it the other way. Doing a ratio. If I did it that way, well then I'm looking for, I got 2.4 moles of Fe2O3, put that underneath there. I'm looking for moles of CaO, put an X under there. So that's going to be 1 over 2.4 equals 3 over X. Cross multiply, 1X equals 7.2. Divide both sides by 1, you get 7.2. Same answer. Pick which method works best for you. One last thing before you work on the problems. I want to go over one more balancing reaction just to make sure everybody understands that. I draw my line down the middle. This is made up of iron, lead, nitrogen, and oxygen on both sides. I have, if I start counting on the left, I have 1. Lead, I have just 1. Nitrogen, I have 1 on the inside times 4 gives me 4. Oxygen, I got 3 on the inside of the parentheses times the 4 on the outside gives me 12. On the right side, I have 1 iron. Pb, I have just 1. Nitrogen, I have 1 on the inside times the 3 on the outside gives me 3. Oxygen, I have 3 on the inside times the 3 on the outside gives me 9. So when I balance this out, first, if I want to try to balance out my nitrogens with a 4 and a 3, I can use the least common multiple. 4 and 3 is 12, so I'm going to have 12 nitrogens on each side. So on the left, I would need to put a 3 right here. That's going to change my leads to 3. Nitrogens already have 4. 4 times 3 is going to give me 12. Oxygens, I have 12 to begin with. 12 times 3 is going to give me 36. Alright, then I go to the other side, my nitrogens, and I got 3. I need to put a 4 in front of there to have 12. That's going to change my irons to 4. It's going to change my nitrogens. I have 3. Now I got 3 times 4 for 12. Oxygens, I have 3 times 3 is 9. 9 times 4, the coefficient there is going to give me 36. So that balances that out. Now I go back to my irons. I got 4 on the right, I need 4 on the left. I put a 4 there, changes that to 4. Lead, I got 3 on the left, I need 3 on the right. If I put a 3 there, that balances that out. So sometimes these are, be careful the ones with the parentheses when you're balancing these out. If you can balance this one, you'll be able to balance any of them that I give you to do these types of problems. And I'll avoid giving one like that was part of the notes there that was, too aggravating to balance. Now your assignment is to do the mole-to-mole stoichiometry worksheet. Number 1, you have like 6 problems to do.